Welcome you all to the online IRENA seminar series. So we are very pleased to have Professor Ian E. Roederer today as our speaker for this talk. So let me introduce Professor Roederer. After earning BS degrees in physics and astronomy from Indiana University in 2005, Professor Roederer earned MA in 2007 and PhD in 2010 in astronomy from the University of Texas at Austin. He was a Carnegie Fellow at the Carnegie Observatories in Pasadena, California, 2010 to 2013, and a research professor in the astronomy department at the University of Michigan from 2013 to 2023, before joining the faculty of the physics department at the North Carolina State University in 2023. So Professor Roederer's research addresses fundamental problems in nuclear astrophysics and near-field cosmology. He uses stellar chemistry to understand the formation and evolution of the Milky Way, the local group of galaxies, and also, most importantly, the origin of the heaviest elements. His work is based on the analysis and interpretation of high-resolution spectroscopy in stars, the oldest stars. He's best known for observational studies into the nature of the astrophysical R process, which is one of the fundamental ways that stars and stellar remnants produce the heaviest elements found in nature. I could go on, but I'll let Professor Roederer take up the stage. And Ian, whenever you're ready, we're very happy to have you and look forward to this very exciting next 1 hour.
Great. Thank you so much for that long and kind introduction. And thank you, all of you, for the invitation to be here and for joining us today. It's fantastic to see so many folks in the audience, many of whom we were chatting beforehand I've not seen in many years. It's so great to see you all again. And also new folks I haven't met in several years either. So it's great to have all of you here. And I look forward to chatting with you, to continuing this conversation after the talk through questions or comments, whatever forum seems appropriate for this. But again, just thank you for being here. And today I'd like to share about what I think is so exciting about this field and what we're learning about the origin of the heaviest elements. I will definitely come at this from an observational perspective, but there's so much great work being done on the theoretical side, the simulation side, and even just in many different observational approaches that are different from the one that I take. There's so much exciting work that has been going on in this field for a while, and I'm just happy to be a part of it and to explore this with all of you. So just as a brief outline today, I'll introduce some of the big questions in this field. We'll talk about one particular old star where we have, well, I don't know if it's a new trick or not, but certainly some new information that we have not had previously for other stars. I'll talk about a recent discovery that potentially has identified some fission fragments in stars. And if we have time, I suspect we won't, but just in case, I went ahead and put here dwarf galaxies and neutron star mergers, and then just sort of a general, what am I so excited about in terms of resources that are going to be coming online in the next few years, next few decades even, that I think can really make some amazing advances in this field. So I'll start with something that we all have seen before. And but one of the things that has been so exciting was the merger of a pair of neutron stars detected both in gravitational waves and in electromagnetic radiation. This was GW 170817 back in 2017, of course. And the piece of this that I'm going to focus on here is the electromagnetic counterpart that is that torus down in the center. So here's the sort of the zoom in around that many of us know as a kilonova, and many of us are familiar with this as sort of one of the sites where heavy element nucleosynthesis can take place in the universe. Not just GW 170817, but other neutron star mergers. And that torus, that glowing, I don't know, aquamarine green donut around the merger remnant is glowing, is powered by a few hundredths of a solar mass of freshly produced heavy elements. And studying those elements is what I enjoy doing as part of my research. And that's mainly what I will be talking with you about today. When I talk about heavy elements, I will mainly be referring to the elements listed along the bottom 2/3 of the periodic table. So these are the elements produced in neutron capture reactions. And just to remind ourselves what neutron capture reactions are, if you have two heavy nuclei trying to come together, or even one heavy nucleus and some other charged particle, that charged particle reaction is not going to be an effective way to produce a new heavy element, a heavier element, because the Coulomb barriers are just too high. But neutron capture reactions, where that neutron does not see the Coulomb barrier, that's how you do this. So neutron capture reactions are the dominant form of nucleosynthesis for the bottom 2/3 of the periodic table. And our process nucleosynthesis, or the rapid neutron capture process, R for rapid, that's one of the major ways that stars and stellar remnants produce those heavy elements. It's the neutrons relative to the typical decay timescales. This almost certainly requires some kind of explosive environment with high neutron densities. The R process is the dominant source of most of the heavy elements that we find in most of the oldest stars. And ancient R process events and other stars produced about half of the heavy elements that we find today in the sun and on the Earth. So we can watch an animation of the R process on this chart of the nuclides as it runs along. So you'll watch this flow, sort of the colored band there. I'll start the simulation, and you can watch that flow up from light nuclei to heavy ones. And that happens something on the order of a second. And then once that flow of neutrons shuts off, all of those heavy radioactive nuclei will beta decay, or other forms of decay, back to stable ones. As we said, the R process is the dominant source of the heavy elements in the oldest stars. So some site or sites capable of generating this flow, generating this huge supply of free neutrons in an explosive environment, had to be operating in the early universe and then continuing across cosmic time until the sun was born, approximately 9 billion years after the Big Bang, giving us the R process material that we find today on the Earth. There are lots of different ways to motivate this. We can certainly start from the US Astro 2020 Decadal Survey, and that survey identified 3 big themes that are ripe for discovery in the 2020s, and we've seen some of this already. New messenger as new physics, worlds and suns in context, and then cosmic ecosystems. And studying this R process touches on all 3 of these different themes. How does it do that? Well, some of these big questions relate to just a general, how did we produce all of these very heavy elements on the periodic table, trying to identify which site or sites are responsible, and do observations require additional sites beyond neutron star mergers, which I think of in the field as like the one confirmed site, because we all watched GW 1708-17 occur, and there's a general consensus that the R process occurred there, but maybe there are other sites that observations say must be required in some way. And then for any of those sites, what are the detailed physical conditions of those sites, right? At some level, maybe that's really what we're after here, the detailed physics of what's going on. And everything else really is just part of the narrative to get us there. Once you understand something about that R process, the formation of those heavy elements, you can use that to help guide your understanding of so many other things. For example, stellar physics in the early universe, the first generations of stars and the earliest generations of stars after that. The hierarchical assembly of our Milky Way galaxy and the stellar structures around it. The distribution of metals within the interstellar medium and then out into the intergalactic medium as well. the heat budgets of planets. This is the one where it touches on like worlds and suns in context. A lot of the heat budget of rocky planets comes from the radioactive decay of heavy elements produced by the R process. So it touches on that as well. And then stepping back from the astronomy side and going more to the physics side, there's a lot of interesting nuclear physics that you can learn by studying heavy elements in stars and the R process in stars, because it gives you potentially constraints on those physical processes and the physical conditions of locations, constraints that you cannot get, at least not at this time, from our experiments, nuclear experiments here on Earth. Here's maybe the one slide way you can build some intuition about how this might work. The abundances of the elements that you observe in the universe, or the amounts of the elements that you observe in the universe, can be thought of as some product of the nuclear properties and the physical conditions. If you know any two of these, you can deduce a third. So if the nuclear data are known, and then you derive the abundances in a suitable star or whatever, then you can infer the R process conditions at that site or the sites that contributed to what you're seeing. Now, there are challenges here, right? The nuclear data are not known for the vast majority of these elements, but that's changing, and I'll mention that later. That situation is improving, thanks to some of you on the call. The abundances of the elements are still growing in terms of how many elements we can detect and how many stars in how many different environments in our galaxy. But they're still limited. There are still uncertainties in the derivation process. And so there's always room for improvement with more data, right? That's sort of the observational rallying cry. We need more data. So there are still limitations into what we can do here. But what I hope to show you today is that in the last decade, we have made some substantial progress on the observational side as it pertains to the R process in metal-poor stars that have allowed us to make some advances that even when I started working in this field about 20 years ago, I wouldn't really have thought to do. So there's a lot of interesting things that are going on right now. I'm part of a group called the R Process Alliance, and most of the work that you're going to see today was produced as part of this collaboration. This is an interdisciplinary collaboration from folks from the communities on this call in many cases, folks with an interest in solving the big questions related to the R process. And if we can raise some new questions as part of that study, all the better, right? There's always more to learn. The more we know we need to learn about the universe and want to learn about the universe. Okay, so brief introduction. I know a lot of us on the call here today are not stellar spectroscopists, so I'll try to give you sort of a brief couple-minute introduction here to the kind of work that I do and that stellar spectroscopists do to turn that amount of faint light coming from some distant star into the meaningful abundances that we publish in tables and in papers in AppJ. So the figure that you're seeing here is a high-resolution optical spectrum of a cool star. And this spans the extent of the visible part of the spectrum, everything your eyes can see, and then a little bit more. And all of those dips, so basically every bump and every wiggle, let's just say it that way, all of the bumps and all of the wiggles in the spectrum are real. They all correspond to absorption lines, and the vast majority of them correspond to absorption by elements in the atmosphere of this particular star. And if we zoom in, the star has a phone number, HD 222925. If you zoom into one little piece of this optical spectrum, you'll see why this particular star is one that I'm showing you here as an example. So you're looking here at wavelength versus flux. That's the spectrum. And there are two spectra shown here. The black line is HD 222925. And the gray line is another star with otherwise similar properties. So similar temperature, surface gravity, pressure, and similar overall amount of most of the elements in this star. Except what you'll notice is that the spectra of these two stars are actually quite different. And all of the lines that are labeled in red are lines of heavy elements. And the absorption is stronger. The dip is deeper in the spectrum of HD 222925 than the comparison star. And that tells us that the abundances of all of these elements are substantially enhanced in this star. So the four ingredients that we need to turn what you're looking at into a table of abundances is, well, of course, you need the observed spectrum. So that's the observational data. You need a model for the stellar atmosphere, so the conditions that are present. You need the atomic data for all of the elements that are relevant. And you need a radiative transfer code to sort of put those ingredients together. And when you do that, this is what comes out of your analysis. So we'll look at several figures like this today. So I want to walk us through just the basics of what you're seeing here. This is log of the abundance, which you can think of as another way of saying the number density of the elements versus the atomic number. For stars, in the vast majority of cases, the only information that we get is the elemental sum of the isotopes that are present. For most cases, you don't get isotopic abundances, so that's unfortunate, but that's what nature gives us. We don't have any way to travel to the star, and the conditions that are present in the stellar atmosphere don't allow us to probe things at the isotopic level. But this is log of the abundance versus atomic number, and the black dots represent the derived abundances for each of these elements in this star, and the different lines represent some comparisons, and we'll use those to sort of help guide our eye as we go through. The two lines that are shown here are both inferred based on solar system material. So the red line is the inferred solar system R process residual pattern, and the blue line, the thinner line, is the solar system S process contribution. So very briefly, the way you do this is you start with the total amount of elements in the solar system. You can go out and count them in appropriate meteorites. So you do that at the isotopic level. You subtract off what you think the S process contribution should be, because there's a quasi-analytic way to do that. And then whatever's left, you attribute to the R process. It's an imperfect way of doing this, but this is what we have. And then you sum up those isotopes to give you the elemental abundance pattern. There are other patterns that we find in metal-poor stars, old stars. The R process is not the only one. It's not the only nucleosynthesis process that can produce heavy elements. There's the S process as well, the slow neutron capture process. There's the, pardon me, the weak R process, or limited R process, depending on how you want to call that. There's also something called an intermediate nucleosynthesis, intermediate neutron capture process, an I process, and then variations on all of these themes. And the point to take away from this slide is that when you plot log of the abundance versus the atomic number, and you have detections and abundances derived from many different elements, it's relatively easy to distinguish between these different processes. Most stars show composite signatures of these processes. So ideally, you want to go to a situation where you can identify just one of these processes as having been the dominant source of the heavy elements in that star, rather than trying to disentangle the different contributions from those different processes. So this is what we do. We derive abundances in stars. We try to identify interesting stars to study. We don't just randomly select them. We try to identify ones that are going to be potentially interesting and give us potentially sort of outsized insight into what's going on with these different nucleosynthesis processes. That's how we choose our stars at some level. The R process that you observe or that you observe out in the universe is probably more extreme than the R process that you can produce on the Earth. The conditions of the R process are just too extreme to reproduce, like one-to-one in a laboratory. So the figure that you're looking at here, rather the image that you're looking at here, is an aerial view. It's a photograph taken looking down on a piece of the Earth. So this is a region called the Yucca Flats in the Nevada test site. This is government property in the Western United States. It was built on Western Shoshone land. And over the course of several decades in the 20th century, more than 1,000 nuclear devices were detonated here, mostly below the ground. And 23 of those tests were dedicated to producing and studying the heaviest radioactive isotopes possible. So in effect, they were trying to recreate some part of this R process. But even so, that was an imperfect recreation because the conditions associated with the R process in space and stars typically occur over longer timescales and at higher temperatures. So you get some information from these terrestrial tests, but it's limited and imperfect. And in any case, the testing program was ended in 1992. But we can study the R process directly in the universe. In fact, in 2017, that was our first sort of widely recognized R process event caught in the act. So that merger of a pair of neutron stars was detected in gravitational waves and all across the electromagnetic spectrum. It occurred not in our own galaxy, but in the outskirts of another galaxy located about 40 megaparsecs away, and that's 120, 130 million light years away, which is still relatively close by astronomical standards. And so we haven't found another one this close at all since then. And we kind of got lucky the first time just because this one is almost in our backyard. But you can see an image of the galaxy there. There's not a whole lot of features in that galaxy. It's a relatively featureless elliptical or S0 galaxy. A lot of old stars in that galaxy, and this event occurred sort of in the outskirts of that galaxy. But we were able to study it all across the electromagnetic spectrum and learn all kinds of things, like associating the R process with that event. And you make that association by comparing the colors and the decay timescales of what you observe with the expected opacities of radiation passing through millions of transitions of all of those freshly produced heavy elements. But even so, you don't get very much detailed information about the element by element composition of what is there. And the figure here helps to illustrate why. So these are model spectra. And as you go from the top to the bottom, you're taking the exact same model and simply changing the velocity dispersion. So the outflow, not dispersion, the outflow velocity of that material away from the neutron star merger event, the velocity of the kilonova as it expands. And if you go from relatively low velocities at the top to relatively high velocities at the top, like tens of percent of the speed of light high, any lines that are present in your spectrum just blur together. So this is heroic work that folks have done to try to tease out what elements are present from the little wiggles that evolve here as time passes. And most of this work was done on sort of archival data because it was done several years later. But there have been some tentative detections of some R process elements as well. So strontium, yttrium, tellurium have all been probably detected here on the timescales of a few days to most like a week or two after that event. And that's great, right? That helps you make that association. But it's not like the detailed element by element mix that you'd want. And even if you look at actual data here, right, you're still struggling to make out more information here than just those few elements. And even by eye, like I don't see them, right? It's relatively complex to model this. And again, the folks who do this are doing heroic work. I'm so impressed by it. But all of that gold and the platinum that you read about in the press releases and all the news coverage from these events, it's all inferred. You don't observe the gold or the platinum or any of that directly in these events. But you can observe those elements and many others in the spectra of old metal poor stars that were enriched by the products of our process events that occurred probably not too far away from where these stars formed in the distant universe. So the spectra here, these are just zoom ins around spectra, looking at the one absorption line of gold that has proven to be a good abundance indicator. It's in the ultraviolet part of the spectrum. So we now have, at least to my knowledge, 6 detections of gold. Shivani Shah added a new one just this year. And there's another one that just didn't publish a figure, so I don't have it here to show you. But to my knowledge, that's the extent of our detections of gold outside of our solar system. It's not just gold, though, right? You get all of these amazing elements from this rich spectrum. So here you're looking at little zoom ins, little postage stamps around some of the R process elements that have been detected in one metal poor star, HD 222925. I've sort of labeled some of these elements, and then of course there are many more that I'm just not showing you here because the screen space is limited. But when you have an ultraviolet spectrum of a star, that allows you to detect many of these rarely detected elements because they just don't show any absorption signatures in the optical or the near infrared spectra that you can observe from the ground. So to get the ultraviolet spectrum, you have to go to space. And right now, the only game to do that is the Hubble Space Telescope. But when you do, this is the rich periodic table that you get, right? When you have the combination of optical and ultraviolet spectra, you get access to, look at this. This is most of the stable elements on the periodic table, all in one star, 65 elements. And to the best of my knowledge, this star currently gives us the best known chemical inventory of any object beyond the solar system. And the different colors here simply tell you where in wavelength space those different elements are detectable. So the red, yellow, and green you can detect from the ground. If it's just in blue, you have to go to space to do that. And the ones that are in that green, this information you get from the ultraviolet spectrum from space really can help improve your measurement to some degree, either by giving you more lines or better lines or something like that. But regardless, right? Look at this rich periodic table that you can get to now start doing some detailed element by element comparisons. So we did this study a few years ago, and given that 50% increase in the number of elements you can detect in cool stars, and specifically in this star, HD 222925, let's look at what that gives us. It gives us a glimpse back into the early universe, a detailed element by element composition of a gas cloud formed shortly after an R process event in the early universe. The general idea of galactic archaeology is that stars live and they die, and that as they live or as they die, sometimes they produce heavy elements or just elements in general, and then return those back out into space where they are formed into the next generations of stars. So as time passes and the gas gets more and more enriched and later stars form, those stars take on, they adopt all of the chemicals, all the elements that were present in the gas from which they formed. So if you can go back to like that second-ish generation of stars, very old stars, you can get a sense of what the very first generations of stars produced. And not just stars and supernovae, but neutron star mergers potentially as well, if those were occurring in the very early universe. So you want to go back to that very old star, or at least ones that show an abundance signature where one event really dominated. So in this case, the one I've been showing you, and I'm going to show you again here, HD 222925, this star shows a heavy element abundance pattern dominated probably by one event. And we were able to detect 42 R process elements in this star, right? That's like most of them, right? There's still a few left, and we're still trying to chase those down. I don't know if we'll be able to or not, but we're going to keep trying. But this is the state of the art for right now. 42 R process elements. So that's 42 elements heavier than zinc, element 30. At least that's how we're defining this. And this gives you a glimpse into what one R process event, one neutron star merger or rare kind of supernova produced shortly before this old star formed. And again, you're looking at the log of the abundance versus atomic number here. Yeah, fine. The key here was that we had ultraviolet spectra from Hubble, because this is a really bright star. You can't just do this for most stars. Otherwise, we would, obviously. We've observed thousands of stars from the ground with optical and infrared spectra, but more depending on how you count. But from space, yeah, we're limited to like a couple dozen, at least with the current technology, to get spectra of the quality you need to derive the abundances of this many elements. Okay, so we did that. Fine. What do we learn from it? That's the important piece here at some level. Well, okay, let's start off by identifying the elements that are new, at least new to the pattern, new to what we can study here. Those are the ones that are shown in the yellow boxes. Those are the ones, at least from the R process, whose elements are best studied from space, from ultraviolet spectra. The red line is that solar system R process residual pattern. And I've just scaled it so that it matches the europium abundance, or you can basically pick any heavy element and scale it to that. All you're doing is renormalizing the amount of the R process to what's in the star. You're not changing the element-to-element ratios at all. So that's to guide your eye. And you'll notice when we do that, there's a really good match between the element-to-element abundance ratios in this star and that scaled solar R process pattern. It's a remarkably good match for the heavy elements. But when you look at the lighter elements, that match is not so good. And it's not that our abundance pattern is necessarily wrong, or that the solar R process abundance pattern is necessarily wrong. They may just be probing different things. So you're seeing the outcomes of different stars that you choose to study. With HD 222925, you're looking at probably the remnants of one R process event, whereas with the solar pattern, you're looking at the cumulative R process events, so like the average pattern that comes out of many R process events that occurred prior to the formation of our solar system. And so there's probably all kinds of new interesting physics to learn here by making these comparisons and recognizing that, oh, we have a new template we can use. We don't have to only use the solar R process abundance pattern anymore. We still can, but we can also use this stellar pattern from HD 222925, and maybe there's something interesting to learn by looking at the differences here. So let's dive into that. Some of the broad implications of this. The differences between the light elements in this star and the solar pattern, that's an interesting thing to study. And this particular study, this was led last year by Erika Holmbeck and colleagues, looked at trying to fit this star's pattern by thinking of it as a new template. If this was all you had to go on for the R process, what would you learn? And one of the interesting things that came out of this study was that, well, it kind of depends on what nuclear physics you choose to adopt in your model, right? So I mentioned earlier that the nuclear physics is unconstrained for some of the properties of some of the isotopes, in fact, many of the isotopes that you would need to run your R process model calculations. And what this study highlighted was that the differences that you would infer from one set of conditions to another in your R process site give you differences that are of the same scale as simply adopting a different set of input nuclear physics. for the otherwise same conditions in your site. So one thing I hope this can do is to help us to prioritize or give some insight into which elements and which measurements of which isotopes could be most influential to help constrain these differences so that these gaps between those different lines are not quite so large if you just have different mass models, for example. So prioritizing nuclear experiment, which measurements should be made or be given priority. So that's one thing that came out of this. Another is that we can use this relatively complete pattern to help guide our interpretation of other abundance patterns in other stars, right? This is not the only one. People have been doing this for 30 years now, right? We've got, at last count, somewhere well over 200 R-process enhanced stars that are known, whose patterns have been studied in various levels of detail. Can we use this star to help to help us get some more information from those other existing patterns in other stars? The answer is yes. And I'm going to apply this to learning potentially something about fission of the heaviest elements in stars because I can, potentially, right? All right, what am I talking about here? The R process is going to produce some very short-lived, very heavy nuclei, heavier than the element uranium, and we call these nuclei transuranic nuclei, beyond uranium. They're the ones that are shown in orange here on the periodic table. One of the dominant decay modes of those nuclei is spontaneous fission. So your nucleus splits into two lighter nuclei, both neutron-rich. It gives off several free neutrons as part of that fission and energy, often in the form of gamma rays. So by studying various pieces of this reaction, you can learn something about the fission process. Those two fragments give me something that I can measure in old stars, right? They go back and repopulate the middle elements near the middle of the periodic table. If this process is actually happening, if they're producing this nuclei and they're fissioning, you're going to be populating the middle of that periodic table again. The R process has already flowed through there once, and now you're going to populate it again, potentially. There's a lot we don't know about fission, and I know many of you who are present today know a lot more about this than I do. I'm just going to highlight a few of the big open questions here. What's the distribution of heavy elements that are actually produced beyond uranium during an R process? How heavy can you go? Where does the R process stop, or where does the fission occur before you can produce the next heavier element? Can you get all the way up to the super heavies, maybe? What else don't we know? We don't know how reliable those nuclear mass model extrapolations are. We'd love to know that. And then for fission itself, what is the final fission fragment mass distribution, at least in the aggregate? That's something we can potentially probe with stars if this is a process that's happening and giving us a signature that we can find. There's a lot we don't know here, but there is also a lot we do know. And I want to just highlight a couple studies here to more or less illustrate a point that, let's see, on the left-hand side, you've got some experimental distributions of fission fragments from individual isotopes. So those are the ones that are listed in the upper left-hand corners of those panels. Just focus on the black dots, ignore all the other lines for right now. That's the experiment on the left. On the right, you have some theory work led by Matthew Mumpower and colleagues. And I'm not going to worry about the details here other than to say that these are theoretical fission fragment distributions for, again, individual isotopes. And the different curves are if you vary one of the parameters in your calculation that governs that fission process. The key thing to take away from this is that both the theory and experiment tend to agree that the fission fragment distributions have sort of this bimodal distribution, a lighter peak and a heavier peak. The details may vary, but that piece, the lighter peak and the heavier peak, seem to be consensus. And again, I know many of you are far more expert on this than I am. I just want to pull out the relevant piece here so that we're all on the same page going forward with what I'm about to show. All right. There's still a lot we'd all love to know about this. And can we use stars to give ourselves some constraints here in a way that we've not been able to do before? Okay, so what did we do? We did a meta-analysis of the abundance patterns of 42 R-process enhanced stars. What does that mean? That means that these 42 different stars, unrelated stars, as far as we know, have had their R-process abundances studied and published previously. And we took all of those abundances and tried to analyze them together as one. So the way that I will illustrate our results here is on the vertical axis, I will plot the log of the abundance ratio of various pairs of R-process elements. And on the horizontal axis, I'll show the europium to iron ratio. Those of you who know what this is know why I'm doing that. Otherwise, just think of this as a proxy for the overall strength of the R-process event that produced the heavy elements that we see in that particular star. It's probably imperfect, but it's a measure that we have. So given those two different variables and axes, if we see a flat trend in this distribution, or sorry, in this diagram, that will tell us that the two elements are being co-produced in the R process. And if there's a positive non-zero slope, that tells us that one of those elements is being produced more than the other one as the R process gets stronger. Okay, so I'm keeping an eye on the time here as well. Here are our results. So I've divided them into 5 different panels, and I've sorted those panels by increasing atomic number. So the elements in panels A, C, and D all exhibit no significant positive slopes. And that tells us that those elements are being co-produced in the R process. And I've chosen to group those elements together in the way that I have by looking at them individually. So here you're looking at the aggregate. But if I only plot one of those elements relative to zirconium or barium and plot it versus europium to iron, you see the same thing. I've just plotted them all together again, so you can kind of see it on one screen and to increase the power of the statistics. What's different is that the elements in panels B and E show a significant positive slope. And that those elements are on the lighter panel, that's B, that's elements 44 through 47, ruthenium, rhodium, palladium, and silver. And for panel E, that is sort of gadolinium and beyond, 64 and beyond. And so the way you might interpret this is to say that maybe the elements in panel B, rather, represent that lighter fission fragment peak, and the elements in panel E represent that heavier fission fragment peak, and elements whose production just naturally requires a stronger R process in the first place. You could maybe try to think of some other explanation for what's going on here. Why is it that B and E show this trend, but the other ones don't? This was the only explanation we could come up with. If you have other ones, I'm totally game to hear them. And let's explore that together. This was the best explanation that we could find given the data that we had. So if that's true, let's go. If that panel B represents the lighter fission fragment peak and E is the heavier peak and elements that require a stronger R process, what does that tell us about the fission of transuranic elements that might be occurring at these R process events? First, it tells us just very simply that production of transuranic nuclei was relatively common in R process events that occurred early in the history of the Milky Way and then later enriched the stars, these old metal poor stars that we are observing today. The R process produced transuranic nuclei. That's one. The next one, you can add up the mass numbers of the fragments and infer the mass numbers of the fissioning transuranic nuclei that gave rise to them. And if you do that, you find that nuclei with atomic numbers, with mass numbers greater than about 260, that they had to be regularly produced in these R process events in the early universe. And just for some context, AF 257 was the heaviest nucleus that was confirmed as a detection in the fallout of these nuclear weapons tests that we conducted here on Earth. So maybe not surprisingly, the cosmic R process events are more extreme than our terrestrial tests. Finally, I think this finding could boost the prospects for actually detecting transuranic element signatures in present-day neutron star mergers. So the figure that you're looking at here shows a prediction. This is a graph showing the absolute magnitude, so brightness, bright at the top, faint at the bottom, versus time. So this is the brightness to light curve after a kilonova, or of a kilonova after a neutron star merger. And the sets of curves at the bottom, the dashed curves, show that light curve if you don't have californium-254 in your mix of elements and have it spontaneously fissioning. And the upper set of curves show that brightness with that fission. And obviously those two sets of curves are offset quite a bit. These are, offset by like 3 magnitudes. That's easily distinguishable observationally by the astronomers. And that gray line across the middle shows sort of the predicted sensitivity of the JWST to neutron star mergers within not just 40 megaparsecs, but 200 megaparsecs in the near infrared part of the spectrum. So I think if this is real, there might be good prospects for actually detecting these signatures in future neutron star mergers that we detect with electromagnetic waves as well.
Yeah, you have like 5 minutes.
Perfect. Thank you. All right. Why am I excited about the next few years or even next few decades? Because the experimental facilities are here. Ariel at Triumph, FRIB at Michigan State, y'all are already measuring some of these nuclei to help fill in those pieces of the chart of the nuclides and constraining our nuclear physics. That's great. I love showing this figure on the right. As you go from bottom to top, you're looking at different histograms versus atomic number. That bottom histogram, the dark blue, is the number of known isotopes that you can reach with sort of the accelerator, the rare isotope accelerators prior to FRIB. That green curve shows you what you could potentially reach with FRIB. And then the top one is what was predicted to exist, right? And FRIB remarkably gets you to most of those nuclei. So whichever ones are most important for constraining the R process could potentially be done in the not too distant future with FRIB, just as time passes and the experiments take time to run, right? It's one laboratory. But that's exciting. We can do this now. That's one piece that excites me. Another is that the next generation of giant optical telescopes is coming soon. In the US, these telescopes take the form of the Giant Magellan Telescope and the 30-meter telescope. Hopefully these will each be built in different hemispheres. If they do, they will certainly have high-resolution optical spectrographs on them that will give you access to the optical and near-infrared spectra of so many more stars in our Milky Way and local group of galaxies than we've been able to examine previously. Another big facility for those of you in Europe or Canada or Brazil is the European Extremely Large Telescope, the ELT. The Andes instrument on that telescope is the high-resolution optical near-infrared spectrograph there. It's designed to do way more than just the R process, right? You can start doing things like nature of the first stars, talk about what sources dominated reionization of the universe, And then, oh my gosh, signatures, biosignatures of life in exoplanet atmospheres, like that's on the table for the next few decades. The science case documents describing all of these exciting potential advances are written. I helped lead one of these exercises. They're out there. You can go read them and think about all the exciting things that we've already thought you might be able to do, and all of the other ones that we didn't think of as part of the process. We're trying to make this, Andes, we tried to, I think the goal here is to make it generally applicable so that it's flexible enough to do whatever science, high resolution optical near infrared spectroscopy you want to do for all the science cases we haven't yet imagined and cannot yet imagine. If you want ultraviolet spectra, right now, Hubble is the only game in town. Hubble's still fully functioning, but it's not going to be there forever. And the next high-resolution ultraviolet spectrograph is going to be on something called the Habitable Worlds Observatory. Used to be known as LUVOIR or HABEX, depending on who you talk to. It's now sort of all fallen under this HWO umbrella. And here's what's exciting. I mean, yes, okay, this is coming for the 2040s, right? The goal is to think about what to do now, build it in the 2030s, launch it, and keep the technology developing so you can launch it in the 2040s. I know that sounds like a long way away. That's near the end of my horizon as well. But what's exciting about this is that we are in the process of defining the science cases that will define the instruments, right? What are the capabilities of the instruments that are going to go on habitable worlds? And if you want to be a part of this, that effort is going on now. Simply search for HWO. You'll find all the science teams, or just contact me. I can put you in touch with the relevant folks. I'm involved in this as well to make sure that to do my best to motivate having a high resolution ultraviolet spectrograph that can do the kind of work we've been describing today. This is very exciting. It's a long way away, but we have to start now, and we can start thinking about this now. So that's a long way to say that I think the future for studying the origin of the elements is bright. There's so much exciting work that we can do now, both for its own merit and to get us where we want to go in the next few decades. And I look forward to continuing to do this exciting work with all of you. Thank you for joining today. Thank you for your time and your attention. And I look forward to chatting with you.